Record.
So good day to everyone. We are Group 5 and we are here to present our coursework 1 regarding machine learning. And first, I'm going to explain task 1, which is data loading and exploration using the California housing dataset. So our plan is simple. First is to explain what our dataset is and what it represents. Second, what insights we want from it. Third, exactly how we loaded and checked it. Fourth, are the key visualizations, histograms, pair plot, and a correlation heat map. And lastly, the takeaways that motivated our later feature engineering in baseline comparison. So we're going to show both the code and the reasoning behind each step. So first of all, what is the dataset? Our dataset is California housing built into Scikit-learn. So each row is a census block group in California. So think of it as a small neighborhood summary. So the columns describe that area. So the column represents the median income, house age, the median house age, then the average rooms and average bedrooms. It is the average number of rooms and bedrooms per household, and then the population and average occup. These are the total populations and the average occupants per household. And lastly, we have the latitude and longitude, which are the geographic location. So the target is med house value. It is a variable. It, it is the median house value in that block group. So our goal is to understand the structure, the quality, and the relationships so we can build a sensible predictive model later. So in this coursework, we aim to answer three big questions. First, is the data usable? That means that the data must be the correct types, it must contain realistic values, and it should have no missing values that we didn't expect. Then second, what do the distributions look like? So sometimes skewed variables, they often need transformation, and outliers may require robust models or engineered ratios. And then third, we want to know how the features relate to each other and the target. So this helps us prioritize which predictors matters and warns us about possible errors in the AI model. So how did we import the dataset? What is X and Y? So we import pandas for data handling, matplotlib and seaborn for plots, and fetch California housing to load the dataset. So the variable X holds all the predictor features. It is the input. And Y, the variable Y, it holds the target that we want to predict. So when I say X and Y, think of it as the input and output. So X will go to the model as a features, and Y is what we ask the model to predict. Then next, what did we check? What does check dataset mean? So when we say check the dataset, we mean a quick health check. So info tells us the data types and the non-null counts. So it is a fast way to catch it. If something is a string, when we need something like a numeric value, or we got an unexpected nonce or no values. Next is the describe. This gives us the summary statistics, like the average, the quartiles, and the spread. It is great for spotting suspicious ranges, like negative ages, which is impossible. The next, we have the head. The head shows a small slice of the actual rows to verify the values look same. Then, finally, we use the isnull.sum, which reports the missing values per columns. So we have found that the dataset shows no zero missing values, which is great, which means that we can focus on understanding patterns without spending time on imputation. I'm gonna drink my water first. So the histogram show how each feature is distributed. So we are looking for a skew, multimodality, and outliers. So in this dataset, we have found that the population and the average occupation look right skewed, with many values and a long tail of large ones. The average rooms show a right tail due to some tracks with unusually high averages. So this suggests that the downstream we might prepare ratio features like rooms per household or per person rather than raw counts. So this matter because skew influences which models and transformations work well. Linear models assume roughly linear relationships and can be sensitive to outliers. If we see heavy skew, then we can consider lagos or engineer per capita ratios. Next, we have the pair plot. A pair plot is a quick way to scan pairwise relationships. So diagonals shows smooth distribution. Off diagonals are scatter plots. So the headline here is Med Inc. and Med House value. You will see a clear upward trend. Average room can show a positive relationship too, but with substantial spread. Um, Next, we have the house age, which tends to be linearly tied to value. So they may be nonlinear dynamics or interactions with location. So the key point here is that pair plots are great for intuition. So if you see a cloud sloping up, that feature is a candidate for being predictive. If it is a blob with no structure, then the feature might need transformation, or simply it may be weak for a linear model. Next is the correlation heat map. So now we quantify those patterns. The heat map shows Pearson correlations between each variables, including the target. So consistent with the pair plot, Med Inc. has the strongest positive correlation with Med House value. You will also notice geographic effects, like with latitude and longitude, related to value, which suggests that location matters. However, location effects can be nonlinear and interaction heavy. A straight correlation won't capture everything. We also glance for multi-collinearity, which is a strong correlations among predictors that can destabilize a linear model's coefficient. So if we saw, for example, a two features that are nearly identical, we might drop or combine them. So the heat maps informs us uh, key features choices, which is to prioritize high signal variables, consider interactions like income and location, to avoid filing in redundant predictors.
So now we will proceed to the future engineering. So the first question is, what type of features did we use? So for our project, we used two main types of features. First is the original features that are derived from the California housing dataset. And the other type are the engineered features. These are the new variables that are derived from the original ones to capture additional relationships. So the other word for the engineered features are the new features. So as you can see in our code right here, the first type of our engineered features are the ratio features. So the ratio features involves the ratio between the average rooms and the date and the average occupation, which is equals to the rooms per household. The second ratio features is the bedrooms per room, which is derived from the ratio between the average bedrooms and the average rooms. The population per household is derived from the ratio between the population and the average occupation. the rooms per person, which is derived from the ratio between the average rooms and the population. And lastly is the income per room, which is the ratio between the med inc and the average rooms. So we also have the polynomial features, as you can see right here. So in our code, the poly refers to the polynomial features transformation, which takes selected original features, which I said earlier, and automatically creates new features like it creates new features that is their squares. So for example, med inc, it will become med inc squared, or house age, which will become house age squared. And pairwise interactions, like the interaction between the med inc and the latitude, and etc. So this is needed so that the linear regression model can capture the trends that are curving and combined effects between the variables that are plain straight lines. It can capture variables that plain straight line terms can't represent. So inside it are all these newly generated squared and interaction columns, which become additional features for the model to learn from. So how did we add them in terms of code? So for the ratios, we created them directly by dividing existing columns. And for the polynomials, we use, which I said earlier, we use the polynomial features from sklearn and preprocessing to automatically generate squared interaction terms. Then concatenated them to the main data frame. So um another question is, how and why did we have to learn the numerical features? So you can see here the code for the scaling of the numerical features. You can see the comment right here. And so we use the scale numerical features because linear regression is sensitive to feature scales, large valued features that can dominate the model's coefficients. And additionally, scaling also ensures that all features have mean, zero, and standard deviation 1, which makes the training more stable and it makes the coefficients comparable. So we accomplished this by using the standard scaler to transform all numerical features except the target. Okay. So another question is, how did we spot any outliers? So for our program, we spotted outliers by visualizing them first using the feature distributions like the histograms and the pair plots. So the extreme values that stood far, okay, so the extreme values that stood far from the data points, yung medyo malayo sa usual na compared to other na data, they are considered as outliers. So how did we remove these outliers? So okay, so we remove these outliers by okay. So we did not remove or modify these outliers, but instead we kept them in the dataset and applied scaling method using the standard scalar function so that the extreme values wouldn't dominate the model. So next question is, how did we verify the correlation of the new features to the output? So obviously we use the correlation function. So you can see here, correlation is equals to. So we created a correlation matrix including only engineered features and the target. So we also used a heat map to visualize how strongly each new feature is related to the Medhouse value. So you can see the heat map right here. The higher the correlation, the more red the color is. So you can see the correlation. The diagonal correlation are always red. And if there is lesser correlation, the color is more blue. So, okay. So based on this heat map, the correlation heat map of engineered features with the Madhouse value shows that some newly created features provide stronger relationships with the target than others. So for example, yung income per room and interaction terms like rent, ink, and latitude exhibit noticeable positive correlations with the target. So this suggests that they could improve predictive performance. So in contrast, features such as the rooms per person and population per household, meron silang weak or near zero correlations. So this means that they are less likely to add predictive value. So additionally, polynomial terms like the house age squared or latitude eh, and longitude appear to have mixed correlations. Some slightly positive, others slightly negative, and depending on how they interact with the target, may contribute very little to the model. Now let's proceed to the task 3. So for the task 3, which involves the debugging challenge of our code. So for what error did you introduce? So for this step, the error that was that the error was that the target variable, the medhouse value specifically, was mistakenly left inside the future set X. So this caused a target leakage, meaning that the model had access to the correct answer during training. So it's not supposed to be uh, on the X. So as a result, the model produced unrealistically good performance metrics. So it produced very high R squared and very low MSE. But this was misleading because the model wasn't really learning patterns. So it's kind of cheating the model. So after spotting this mistake with a debugging check, the fix was to drop the metals value from the features, ensuring that the model only trained on valid predictions. So, wait, saan yung yun off? Ayun, okay. Wait lang, scroll up ka muna. Okay, so you can see here the error, which is the X error is equals to the data scale dot copy. So dapat yung medhouse value is not integrated on the X code because nakaka-affect yan sa sagot or sa Y. So another question is, what was the indication that it has an error? So the indication of the error was that the model's evaluation metrics look too good to be true. So it's not supposed to be near perfect. It achieved an abnormally high R squared and very low MSE. So to confirm this, the debugging print statement, ano yun? Debugging print, ayun. Debugging output, displayed the list of feature columns and medhouse value was still included. So since the target value should never be part of the features, its presence revealed the exact cause of the error. Okay, so how did we address this error? So as I said earlier, we fixed the issue by explicitly dropping the target column, which is the medals value from the features before training. So this ensures that the model only learned from the independent variables like the med ink, house age, etc., and not from the answer itself. So by doing this, we eliminated the problem or the target leakage and made the model's evaluation metrics realistic and trustworthy. So that is all for task 2 and 3. Let's now proceed to task 4.
Okay, so for task 4, it is now the part where we will train the model and evaluate if the model that we have created using the new engineered features performs better or worse uh, compared to its baseline model. So firstly, here We've imported some sklearn's functions, such as the linear regression, mean square error, R squared, and the train test to get the values later on. So firstly, what we did here was we used the baseline model, which is essentially, again, using only the independent, or what we had been saying as the x variable. Only the original features was included, so there was no engineered features. And then now we're going to use the y, which is the Medhouse value, which is the one that we want to predict. So using this function, the train test split, we were able to split the test size into 0.2. So now using the model underscore base linear regression, we use this to evaluate, not to evaluate, but to train the model or fit the model so that it will use this independent variable to train the y, or to train so that it will get the uh, base y output. So now when we use the y predict base using this predict function, we will be able to see its performance based on its mean square error value and the R squared score. So using the baseline values only, or baseline variables or features only, you were able to get a value of R squared of around 579, and the baseline MSE of 0.55589. So now, since we are going to compare it with the one that we added the engineered features, we will be able to see here that using this new x and y variables, which we explicitly stated to drop the Medhouse value first, and then after we train it here using the train test, after we split the data set again with the size of 0.2 for the test file, you will see that after the same process but with a different x input, you will see that when we compare the two models, the new one with the engineered features performed better in its based from its R squared value. So originally it was 0.5758, and now it performed a little bit better to a 0.68459. And the MSE also dropped from 55 or from 0.55 to 0.41, meaning that the engineered features actually improved the model. So here is the whole code for that peer evaluation. So from there up to here. And then from there, we wanted to actually visualize or to see what was the prediction that the model was doing compared to the baseline model that we made. So this is the actual scatter plot, or the plot that was being used. So the blue dots shows or are the baseline predictions, which is, as you can see, there's already been a outlier here and more outliers here. While the red one, the engineered feature predictions, show a more closely grouped prediction or dots, red dots here, and which also follows the trends, which also better follow the trend of this perfect prediction where the y is equal to the x. So going back here, this is essentially the code for the line plot and all of the other code so that it can be visualized into these figures. And so that's it. That concludes Group 5's review and discussion of this coursework.